You know, the peptide market right now is just absolutely flooded with claims about accelerated recovery, but separating the hype from reality, that means looking strictly at the data. So our explainer today is focusing on TB-500. It's a synthetic peptide fragment that sits right at the absolute center of tissue repair research. We are going to look purely at the verified clinical data and the exact biological mechanisms documented in the scientific literature. We're talking real-world dosage protocols, safety profiles, and exactly where it stands legally right now.
Right off the bat, there is a critical structural distinction here that is constantly misunderstood out there. Thymosin Beta-4 and TB-500, they are not the same thing. Thymosin Beta-4 is a naturally occurring 43 amino acid protein. It's found in nearly every cell in the human body, and it actually carries a pretty substantial history of human trials. TB-500, on the other hand, is a highly specific, lab-made 7 amino acid fragment. Think of it like an exact copy of positions 17 to 23 of that larger protein, specifically the sequence ACLKTEQ. This is crucial because when we look at the major human trials for wound healing and heart recovery, researchers were testing the full-length 43 amino acid protein, not the shorter TB-500 fragment.
And actually, this leads to a brand new layer of complexity that was just uncovered in a 2024 study by Rahman and colleagues. They found that once TB-500 enters the system, it rapidly breaks down into an even smaller active metabolite called ACLKKT. What's totally fascinating here is that this tiny metabolite is the thing that retains wound healing activity in experimental models. If future research keeps confirming these findings, it suggests that TB-500's biological effects might actually be mediated by this even smaller broken-down fragment rather than the originally injected peptide itself.
So how does the actual cellular repair happen? Well, you have to understand actin. Think of actin as the scaffolding that cells use to move and change shape. TB-500 has this powerful affinity for the G-Actin form. By binding directly to G-Actin, the peptide maintains a ready, available reserve pool of it. This essentially allows repair cells to efficiently build their internal structure and migrate directly and rapidly toward damaged tissue. Once those cells arrive at the injury site, they trigger the whole tissue repair process, promoting new blood vessel formation and collagen production.
When we audit the clinical evidence, we have to firmly separate what has actually been tested in humans from what relies strictly on animal models. There is ample human clinical evidence for the full-length Thymosin Beta-4 protein delivered as eye drops or skin treatments. We're talking specifically about corneal wound healing in Phase 3 trials and cardiac repair in Phase 2 pilots. However, when we shift to applications like tendon or ligament repair and neuroprotection, the evidence for injectable TB-500 rests entirely on animal models.
To put that human data into perspective, let's look at the exact statistics from the strongest evidence we have, which is wound healing. In the SEER-1 Phase 3 clinical trial, researchers tested a 0.1% eye drop version of full-length Thymosin Beta-4 on patients dealing with a severe condition called neurotrophic keratopathy. At 4 weeks, exactly 60% of treated patients achieved complete corneal healing. That's compared to just 12.5% in the placebo group. Now, it is important to note that this trial narrowly missed conventional statistical significance for its primary endpoint at p equals 0.0656, so it almost but not quite hit the gold standard threshold for proof, though the investigators did describe it as a strong positive trend.
On the cardiac side, a 2025 study by Marr and their team mapped out exactly how this prevents heart scarring. It's a really interesting mechanism. By increasing a genetic regulator called MIR1395P, the peptide suppresses a protein known as ROC1. The result of that? It physically stops healthy tissue cells from transforming into rigid, scar-producing cells. That process is scientifically known as fibroblast to myofibroblast transformation, and it's exactly what causes cardiac fibrosis and heart stiffness.
Shifting our focus over to physical injuries, the animal data is quite compelling. A 2014 study examining rat Achilles tendons documented precisely a 34% increase in collagen building and improved tensile stretching strength after treatment. Across various animal models, researchers observed that the new collagen lined up better and rebuilt faster. This was driven by consistently higher levels of VEGF, which is a protein that triggers new blood vessel growth, specifically inside oxygen-deprived tendon tissue.
But there is a very crucial caveat that we absolutely must emphasize here. Despite the highly promising animal data regarding structural rebuilding and collagen production, absolutely no controlled human trials exist for TB-500 when it comes to tendon or muscle repair. None. Athletes and users who are utilizing TB-500 for musculoskeletal injuries are doing so entirely based on theoretical applications and preclinical animal data.
We see a very similar pattern in neurological research. A 2018 review by Morris and colleagues looked at animal stroke studies and documented some clear benefits.
In younger rats treated with the peptide, neurological scores measuring movement and brain function actually improved by 24% to 35%. But even more remarkably, in older rats, the actual physical size of the brain injury was reduced from 26.04% down to 12.77%. That is a reduction of about 51%. But again, keeping things strictly factual, there is currently no evidence confirming these precise outcomes translate to human brain recovery.
Another application gaining heavy community interest right now is hair loss. A 2015 study by Gao et al. Demonstrated that the peptide activates stem cells inside hair follicles. In these animal models, the treatment successfully pushed the hair follicles out of the resting telogen phase directly into the active growth anagen phase. It even visibly increased the physical size of the follicles. But just like with muscle repair, we have to remember that this data is limited entirely to animal models right now, with no controlled human data confirming these results.
So how is this peptide actually being used in the real world? Well, because there are no FDA-approved dosing guidelines, the current protocols are entirely community and practitioner-reported. For subcutaneous injection, the commonly reported loading phase is 2 to 2.5 milligrams administered twice weekly for 4 to 6 weeks. Some users do utilize more aggressive loading phases of 4 to 5 milligrams twice weekly. This is then typically followed by a maintenance phase of 2 milligrams once weekly. A standard cycle length runs 8 to 12 weeks, and that is followed strictly by a 4-week break.
Now, a fundamental characteristic that sets TB-500 apart from other peptides like BPC-157 is systemic distribution. Unlike other well-known repair peptides which primarily operate locally near the injection site, TB-500 circulates systemically through the bloodstream. This means that administering site-specific injections near your injured shoulder or knee is entirely unnecessary. The peptide will act on multiple injury sites throughout the body simultaneously, regardless of exactly where the subcutaneous injection occurs.
When you track the exact user-reported recovery timelines chronologically, a clear pattern really starts to emerge. Anti-inflammatory effects are often observed in the first week. For acute injuries, users generally report improvement starting around weeks 3 to 4. Because tendon and ligament injuries lack direct blood supply, they take a bit longer, showing noticeable improvements between weeks 6 and 8. And then long-term, stubborn chronic injuries typically require the full 10 to 12 weeks of the cycle to exhibit significant repair.
While Phase 1 and 2 human trials of the full-length protein showed it to be generally well-tolerated with mild temporary adverse events, there is one critical medical contraindication you need to know about. Because of TB-500's potent pro-angiogenic properties, meaning its ability to stimulate the rapid growth of new blood vessels, researchers strongly advise against its use by anyone with active or suspected cancer. The reasoning here is that generating new blood networks could theoretically feed malignant cells.
We also need to document the strict legal reality as of June 2026. TB-500 is not a controlled substance in the US, but it is definitely not FDA approved for human use. On April 23, 2026, the FDA officially removed it from its Category 2 list. The most pivotal upcoming date is July 2026, when the FDA's Pharmacy Compounding Advisory Committee will review TB-500 for possible placement on the 503A bulks list. That decision will dictate whether licensed compounding pharmacies can legally prepare it by prescription going forward, which is going to drastically change how users can access it.
And for competitive athletes, the regulatory rules are absolute. TB-500 is explicitly prohibited under Section S2 of the 2026 WADA prohibited list. A positive test will trigger a minimum 2-year ban from competition, and that can actually escalate to a 4-year ban if intentional use is established. It is vital to understand that current anti-doping testing methods carry a detection window capable of identifying TB-500 in blood and urine for roughly 30 to 45 days after use.
Because of this transitional legal status, most procurement happens on the gray market, and that presents some significant practical risks, including contamination and wildly incorrect dosing. Because of this gray market reality, establishing safety requires strict due diligence from the buyer. The practical cost floor for a legitimate, quality-controlled 5 mg vial sits between $30 to $50. But price alone doesn't guarantee purity, making an independent third-party certificate of analysis the absolute minimum standard required to verify exactly what is inside the vial.
As clinical trials progress and that July 2026 FDA review approaches, we are really left with a fascinating clinical question. Given that peptides naturally break down in the body, will the future of regenerative medicine rely on harvesting the entire full-length, 43 amino acid natural protein? Or will it be defined by harnessing these precisely engineered, highly concentrated active fragments like ACL-KTE? The outcome of this research is going to entirely reshape how we approach tissue repair.